Power begins with knowledge. From the hum of a generator to the precision of a control panel, every connection matters. Learn, adapt, and keep the current moving.
At its core, an electrical fault is an escape. It is an abnormal condition that allows current to break away from its intended insulated path and seek its own low-impedance route back to the source. The absolute highest potential fault a system can physically generate is a three-phase symmetrical fault. If all three active phase conductors make direct physical contact, the resulting zero-impedance dead short causes the current to instantly spike to thousands of amps. That balanced fault is incredibly destructive, but relatively rare. Over 95% of real-world failures are unsymmetrical faults. The most common is a line-to-ground leakage, where a single energized phase conductor rubs against a grounded metal chassis or structural beam due to failing insulation. If the hardware fails to clear these faults immediately, the physical consequences scale up rapidly. A sustained overload leads to progressive thermal melting of wire insulation. A dead short circuit releases a massive, instantaneous energy spike, resulting in localized structural tracking fires or explosive arc flashes. Containing these threats requires us to isolate the damaged circuit faster than the physics of the fault can destroy the surrounding infrastructure. Doing that has required a complete evolution in how we build protective hardware. We have had to move from basic sacrificial materials to dual-stage electromechanical latches, precision mathematical differential monitoring, and finally to completely solid-state logic gates. The difference between a localized trip that you reset in your hallway and a catastrophic electrical fire comes down entirely to the microsecond reaction times of these exact hardware architectures. The baseline technology for containing runaway current is the sacrificial fuse. Placed directly in series with a load, it serves as an intentional weak link in the electrical chain. The fuse operates entirely on the heating consequence of current. As electrons flow through the calibrated internal metal link, they encounter electrical resistance. The heat generated by this friction is calculated precisely. Power equals current squared multiplied by resistance. During normal operation, the heat generated by the element is safely absorbed by a filler material packed inside the fuse casing, typically porous quartz sand, which conducts the thermal energy away into the surrounding air, allowing harmless loads to run continuously. But if we overload a circuit by plugging in too many devices simultaneously, the system enters a sustained overcurrent fault. The heat generated exceeds the rate at which the surrounding sand can dissipate it. It crosses the element's specific thermal energy capability, its I²T rating, and the metal wire begins to glow. As the temperature rapidly scales, the internal wire hits its melting point, liquefies, and physically vaporizes. This destruction leaves an open-air gap inside the cartridge, entirely severing the current flow. The sand absorbs the final arc energy. The engineering is highly effective because it uses the fault's own thermal physics against itself. The limitation is finality. Because the internal conductive channel is reduced to gas and slag, the device cannot be reset. It must be discarded. Industrial scale and modern residential infrastructure cannot rely on constantly replacing vaporized metal. We needed a device that could mimic the physical interruption of a fuse, but do so with non-destructive, resettable mechanics. The miniature circuit breaker, or MCB, solves the replacement problem by operating as an automatic mechanical switch. Rather than destroying itself, it uses dual-stage logic to map internal hardware to specific fault profiles. Stage 1 is thermal operation, designed to catch the exact same progressive cable overloads that would melt a fuse. Inside the MCB, the current passes through a calibrated bimetallic strip, two joined metals with completely different expansion coefficients. As excess current causes continuous I²R heating, the two metals expand at uneven rates, forcing the entire strip to physically bend. Once the deflection hits a critical physical angle, it releases a mechanical latch that forces the main contacts open. That thermal bend is perfect for slow overloads, but a dead short circuit requires immediate interception. That introduces stage 2, magnetic operation. Looking at the internal schematic in the closed position, you can trace the load path directly through the second sensing component, the magnetic element, or solenoid. When a short circuit hits, the massive instantaneous spike in current rushes through the wire coil of that solenoid. Because magnetic field strength is directly proportional to current, this creates a powerful magnetic field instantly. The field generates immense physical force, driving an iron plunger forward like a piston. It strikes the trip lever directly, releasing the latch mechanism and violently separating the contacts. This mechanical sequence occurs in less than 10 milliseconds. A specialized internal arc chute matrix catches the resulting electrical arc and stretches it until it extinguishes safely within the plastic housing. The MCB is a brilliant piece of dual-stage hardware. It protects wires from melting and isolates short circuits before they explode. But its physical latches require massive volumes of current or heat to trigger. Because of this high activation threshold, the MCB is completely blind to low current anomalies. If a person touches an exposed wire, a line-to-ground fault occurs through their body. The current required to stop a human heart is a fraction of an amp. A standard 20 amp MCB will never detect this. The current volume is too low to bend the bimetallic strip or trigger the magnetic solenoid. To protect biology instead of copper, we rely on the residual current circuit breaker, or RCCB. Notice the print on the housing. It has a rated sensitivity of just 30 milliamps. The RCCB achieves this by abandoning heat and magnetism entirely. It operates exclusively on differential current monitoring. The logic relies on Kirchhoff's current law. In any closed loop, the exact amount of current entering the circuit on the active line must equal the amount of current leaving the circuit on the neutral return. Inside the RCCB, we see the toroid, a core balance current transformer. Both the incoming line phase and the outgoing neutral return pass directly through the center of this magnetic ring. Under normal conditions, 50 amps flow out and 50 amps flow back. The magnetic fields generated by the two wires are equal and opposite, meaning they perfectly cancel each other out inside the toroid. The net magnetic flux is zero. Now introduce the fault. If a wire frays and current begins leaking to an earth ground or through a person, the math breaks. 50 amps leave on the line phase, but only 49.97 amps return on the neutral wire. This 30 milliamp vector imbalance leaves residual magnetic flux inside the toroid. That flux immediately induces a tiny voltage in a secondary winding coil wrapped around the ring. This induced voltage energizes a high-sensitivity relay, commanding the breaker to trip and sever the circuit. The RCCB intercepts lethal touch potentials exactly because it monitors mathematical flow rather than physical limits. It is a device built to prioritize human life. Fuses vaporize. MCBs and RCCBs rely on moving iron plungers and mechanical latches. Over thousands of cycles, mechanical parts degrade. More importantly, physically pulling two conductive contacts apart inherently draws an electrical arc for several milliseconds before the circuit is truly broken. The modern ceiling of circuit protection requires eliminating moving parts entirely. That brings us to the solid-state electronic circuit breaker, or E-breaker. E-breakers abandon metal contacts in favor of high-power, wide-bandgap semiconductors. Specifically, they utilize silicon carbide MOSFETs, or isolated gate bipolar transistors, to act as the gatekeepers of the current flow. Instead of waiting for a metal strip to bend, the E-breaker continuously monitors the active current using highly precise Hall effect sensors, or shunt resistors. During normal operation, an active bias voltage is applied to the semiconductor's gate terminal. This input creates an internal highly conductive channel, allowing the electrical load to pass through the silicon architecture seamlessly. The moment the sampling circuit detects the leading edge of a short circuit spike, the internal logic gate removes the bias voltage from the terminal. Without the bias voltage, the silicon channel instantly shifts from highly conductive to entirely non-conductive. There are no latches to swing or springs to release. The total interruption occurs in under 1 microsecond. This is thousands of times faster than any mechanical breaker, halting the current before an arc forms. The modern electrical grid is not protected by a single omnipotent device. Safety is achieved through a layered architecture, mapping specific hardware configurations to distinct physical threats. This matrix outlines how that hardware is deployed. We use sacrificial fuses and thermomagnetic MCBs as the primary bulkheads against infrastructure damage, manipulating heat and magnetism to stop wire degradation and short circuits. We overlay that system with differential RCCBs, relying on continuous Kirchhoff balances to intercept the tiny leakages that cause biological harm. And at the absolute peak of modern power demands, we substitute mechanics with solid-state silicon logic, eliminating physical degradation and arc flashes entirely. The grid is evolving. We're shifting from predictable linear loads to direct current infrastructure, rapidly charging massive battery storage systems and electric vehicle networks. As we integrate these highly sensitive, non-linear loads across the globe, which of these protection mechanisms do you think will become the most critical failure point in the next decade? Let me know your technical breakdown in the comments below.
Namaste, my friends. Thank you for watching. Remember to like, share, and subscribe for more knowledge, and keep learning every single day.